Welcome to Model 9, Machine Learning in the Real World. We start with a trap that catches almost everyone. Imagine a model that is 92% accurate. That sounds excellent. It can also be completely useless. Here are 100 transactions from a payment system. Each dot is one transaction. Almost all of them are perfectly ordinary, 92 legitimate payments. But hidden among them are 8 fraudulent ones. Just 8. 8% of the data, and yet catching them is the entire reason this model exists. Now the laziest possible model. It doesn't learn anything at all. It simply predicts legit for every single transaction, all 100 of them. Let's score it on accuracy, the fraction it gets right. 92 of the 100 are legit, and it calls them all legit, so it scores 92%. On paper, that looks great. But watch what it did to the fraud. Every one of the 8 frauds, it called legit. It caught none of them. 0 out of 8. The one job we cared about, and it failed completely, while still scoring 92%. That is the accuracy trap. To see the whole story, we count every outcome in a small table called the confusion matrix. The rows are the truth, the columns are the model's guess. The lazy model called everything legit, so 92 real legit transactions land here, correctly labeled. All 8 frauds land here, predicted legit, but actually fraud. The caught fraud cell stays at 0. The number that exposes this is recall. Recall asks, of all the real fraud, what fraction did we actually catch? 0 caught, out of 8. Recall is 0%. Accuracy averaged over everything, so the 92 easy cases drowned out the 8 that mattered. It hid the only mistakes we cared about. Surely a real model does better. Let's train an actual logistic regression on this data. It learns a boundary, and flags this corner of the space as fraud. And its accuracy? 95%, even higher than the lazy model. By the accuracy score alone, this looks like a clear win. But we've learned our lesson. Check the fraud directly. Green means caught, red means missed, and yellow means a false alarm on a legit payment. 4 frauds caught, 4 still missed. In the matrix, 4 true catches, 4 misses, 1 false alarm. Recall is only 50%, a higher accuracy, and it still misses half the fraud. Why does a trained model do this? Picture a scale. The model is trying to minimize its total mistakes. On one side sit 92 legit transactions, on the other, only 8 fraud. Against 92, sacrificing a few frauds barely moves the total error. To the model, the rare class is cheap to get wrong, so it mostly ignores it. The fix is to change what counts. We tell the model that each fraud matters 11.5 times as much as a legit, the same ratio as their counts. Now the two sides of the scale weigh the same. A missed fraud hurts the model just as much as many missed legits. The rare class can no longer be ignored. We retrain with those weights. The old boundary was here. The new one shifts down and outward, claiming more of the space as fraud. Now check again. All 8 frauds, caught. Recall is 100%. But look at the cost. Precision drops to 50% because it raised 8 false alarms on legit transactions. Line the 3 models up. Watch the accuracy column, 92, 95, then back down to 92. And the fraud recall column, 0, 50, 100. The best model by accuracy was the worst at the actual job. A missed fraud costs far more than a false alarm, so recall is the metric that matters here, not accuracy. Weighting the rare class is one tool. You can also oversample the minority, creating more copies of it. That's the idea behind the SMOTE method. You can undersample the majority, or move the decision threshold. Different tools, one goal. Stop the rare class from being drowned out. So, on imbalanced data, accuracy lies. Read the confusion matrix, not the average. Choose the metric that matches the real cost. And rebalance, so the rare class counts. Next, we ask a harder question. When a model says it is 90% sure, is that confidence honest?